Up until now, the linear systems that we've seen have all had unique solutions. It's also possible for a system to have no solutions, or the more interesting case of having infinitely many solutions. Now, even a single equation is a system of equation, so let's look at something like x minus y equals 0, which is a system of one equation and two variables. Now, this system admits infinitely many solutions. Here are some of them, and there are plenty more. You can probably see a pattern. And if we rearrange our linear system, we see that every point on the line y equals x is a solution to the given equation. Or if we wanted to write these as pairs of points, xy equals tt is a solution for every real number t. Now there's something deeper going on here. Our solution was a line, and we have two different ways of representing lines. We can provide an explicit equation, in which one variable is written in terms of another. And the idea here is that if you're given a value for x, you can use it to compute the value of the other point y. And the other side of that coin is a parametric description. Here, there is a parameter t which you use to compute both x and y. You don't first compute x and then use it to compute y. So now we're going to focus on things like lines and planes, but let me give you another example of a curve and its parametric representation, just to ensure that you get the gist of how parameterizations work. So here's y equals x to the 2/3, which is a cuspy looking function, and its parameterization is t cubed t squared. On the left, if we plug in x equals 8 into our equation, we get out y is 4, and on the right, to get the same set of points, we use t equals 2, and if we plug that in, we get 8, 4. So, linear systems are often written in this explicit or perhaps implicit form, but we're not going to worry about that. And their solutions as vectors and matrices are written parametrically. All right, so if a system has infinitely many solutions, how do we determine this and how do we write them all down? First, we do our usual thing. We write down the augmented matrix and we row reduce it. In RREF, if there are any columns without leading ones, that's our sign that we have infinitely many solutions. We assign parameters to those variables that don't have leading ones. Then we solve for the variables that do have leading ones and write the answer in terms of those parameters. So we'll do a proper example in a second, but let's say that you're given an augmented matrix that's already in our RREF. We see that there are two columns here that don't have leading ones. Now, normally we'd have a linear system to base this off of, but here let me give the variables names, which I'll just put above the matrix there. So it's x2 and x4 that don't have any leading ones, and let's give them parameter names. Now, to solve for the other variables, let's rewrite this as a linear system. And we're going to solve for x1, x3, and x5, because those are the ones that do have leading ones, and that's going to give us the following. And we replace x2 and x4 with their parameters. So thus we've solved for all of the variables, and we can write out the entire solution. Remember that x2 equals s and x4 equals t are the solutions for those two variables. Okay, so now that we know how to parameterize infinite solution sets, let's do a proper example. Here is a linear system. Let's solve it. Okay, so as always, we start by writing down the augmented matrix, and we row reduce that matrix. So this first step isn't too bad. Let's add negative R1 to R2. And notice now that everything in R2 is a multiple of negative 4, so that's convenient. We can rescale it. And we're currently in row echelon form, but let's go to RREF. And the way that we can do that is taking negative 3 R2 into R1. And if we now we're in RREF, so let's write out our new linear system. And this third column here, the z column, does not have any leading ones. So we're going to give it a parameter, say t. Now we solve for x and y using our system above, and we're going to sub in z is equal to t. And that allows us now to write down our whole solution as follows. Now the great thing is, so we're done, but we can always double check our answers by plugging this answer back into the original linear system. So the first equation was x plus 3y plus 9z, and we're supposed to get 7 out of this. So let's plug our answers in and isolate the terms with t's in them. Okay, great. And what you'll notice is that all the t terms cancel, and they'd better since we need to get the constant 7 out. So the leftover bits do add to 7 as required, and that equation is satisfied. Now we're going to do the exact same thing for the second equation. We should get 3 out. Again, all of the t terms cancel with each other, and the bit remaining is just equal to 3. Great. And that's how we parameterize infinite solution sets.